we've had a couple of classes now on confidence intervals that look at, throwing error bars essentially on means or on averages. And the last piece of the puzzle for us is going to be looking at the common use of percentages or proportions to report statistics and how to throw error bars on that. So the most obvious use of statistics in terms of percentages in the news these days is obviously the things like vaccine efficacy rates, right? That's how they're reporting how effective vaccines are, is they're using percentages. And I posted just an article here recently, just a few minutes ago, that just talks about how they calculate this, right? When you hear that the Pfizer or the Moderna vaccine is 95% effective, what does that mean? How do we make sense of that? Does it mean that 95% of people that are given the shot don't get it? Well, it turns out that's not how they calculate it, but it's close. And this is how they calculate it here. 100 times 1 minus the attack rate with vaccine divided by the attack rate with placebo. So they do what's called clinical trials. And of course, the important thing here is you'd have a double-blind trial, right? We talked about that in chapter 1. It means that neither the doctor nor the patient knows if you're getting the placebo or if you're getting the actual medicine. Right? Double blind means that the experimenter or the doctor and the patient, the doctor and the subject, or the doctor, let's say patient, don't know which vials or which shots or which vials are the placebo. So a placebo is just a fake medicine. Yeah, basically that's enough there. You say neither the experimenter, right, the scientist, the experimenter, and the patient, in this case is the subject, know which vials are placebo. And so what you would do is you would take, let's say, a population of all the people that get it, and they give it to something like 20,000 people over a 9-month period, right? This happens so fast. That's what's amazing, is that they're able to develop these vaccines so fast and show it's effective. How do they do that? Well, you give it to 20,000 people, let's say over a 9-month period. And well, that means that half of them, right, half get the placebo. And you randomly assort them, obviously. This is a random sorting. And then 10,000 get the actual vaccine. And then you have to wait until people get sick. So, they're injecting people, they're part of this experiment. And then what happens is people get sick. And so essentially what they did, and this is the power of statistics that we're going to do here, is that you wait until people get sick. And they waited until the first, I think they had 95 people come in that were sick. Okay, so you had 95 COVID cases of people that were given either the vaccine or the placebo. These are people with symptoms, right? They come in, they have symptoms, they get tested. and they have COVID. And then the question is how many people were in the placebo group and how many people were in the vaccine group? Well, it turns out that the people in the placebo group, it was 90 of them. And the people that were in the vaccine group, it was 5. And this is the results that were released last year, right? So they had come up with this, remember, in like November or something like that. And then all of a sudden they say it's 95% effective. So how did they get that number? So what they did, and they talk about that in the article, if you read that article that I just showed you, the way they calculate it is they go 100 times 1 minus the number of people that were given the vaccine over the number with the placebo. And again, because 90 out of 95 of the people were given the placebo, this looks good, right? It doesn't prevent it. There's another article that I was looking at about an outbreak in British Columbia. I think that's kind of what led me to this to begin with, was, you know, there's an outbreak in British Columbia at a long-term care facility. And they were saying that 8 people had 1 dose of the vaccine. And that's going to be expected, right? You're not going to, it doesn't eliminate transmission, it just decreases it significantly. It's still possible to get the flu after you get a flu shot. And so when you do the math here, what do you get? So let's call this the efficacy of a vaccine. And this can be an ongoing experiment, and that's what they're doing, right? As people keep coming back, they keep measuring this ratio. But initially, when they first made the news, right, you remember it was released, it was big news. It was with this data here. These were the numbers. So they only had 95 people come in, but due to the power of statistics, as we'll see here, this is good. So 5 over 90. You get 94%. That's how they come up with that number. What we want to learn how to do today is throw some error bars on that and get our actual parameter. So when you add the error bars, all of a sudden you're going to get a parameter. Right, you're going to get something, it's going to look like this. Plus error gives you a parameter, and the format in your formula booklet here. So again, because we're dealing with proportions, these are the symbols that we're going to use, or here. So this is the error, this is the calculation of the error, the formula here. So the format is going to be the population parameter equals the test statistic, or in other words, the point estimate that we learned yesterday. That's the word, right? This is a point estimate. It's going to be plus or minus this error. And so according to that formula sheet, the error is given by Z, again, the alpha over 2 that we saw with the means, P hat, Q hat over N. So really it comes down to, again, when you're making your parameters, you have to decide on what confidence interval you want, right? How sure do we need to be? Well, I assume when you're making vaccines that you want it to be as close to 100% as possible. So let's say that's the case, right? You don't want to make a mistake at all, and according to our formula sheets, the highest you can go, right? If you go to your formula sheet and you look up a Z-score, the biggest Z-score that we have here, right down here, this is an important notation. I talk about this in the video that I posted yesterday, but if you want to be, this is if you want to be 99.9% sure, right? You can never be 100% confident because that's setting yourself up for failure. This is so you would use this Z-score here, 3.49. And this is really as confident as you can get. Any more and it's not realistic. So let's use that Z-score. Let's say you want to be 99.99% confident. And then we'll compare this, just for the sake of comparison. Let's compare that to 90% confident afterwards and see the difference in the error bars. Let's do this. So let's take a Z-score of 3.49. What was our P with a hat? 94.4. So make sure you put it as a decimal or else you get the wrong answer. The Q hat is 1 minus. So Q hat is going to be the same thing with binomial. When you have to have P and Q, it's going to be 1 minus P hat. Now the sample size in this case was 95 people. Right, that's how many people came back and were part of the actual, right, there was 95 COVID cases. So they have a population of 95. And let's see what the error is here. Sorry, I'm using my calculator. I used to use that calculator on the website, but I like my TI-83. I've had this thing since I was in high school, 22 years ago. So it's kind of my baby. All right, so the error on this thing is 0.0 823. Now, when you translate that into a percentage, that's like an 8.2% error. Right? That's quite a high error. So that's why they reported this as a preliminary data, right? They said, okay, look, they didn't say that this is for sure it. They have to keep testing it. You're going to want to increase your sample size. When they first reported it, they said, okay, this is pretty good. But let's see what a 90% confidence would look like. Right, let's all of a sudden, let's say, okay, this is 99% confident where you have an error of 8.2%. But what about if you have an error that corresponds to a 90% confidence? So again, this is a 99.9%. But let's say you want to, more realistically, let's say I need a 90% error, a 90% confidence interval, or a 95 or something like that. What is your Z-score there? Right, again, you'd have to look here. So a 90%, it's always good, always draw the curve to make sure you're getting the right Z-score. Okay, so again, a 90% confidence means that there's 5% here, 5% here. So I'd be looking up a value of 0.05 on the formula sheet. Right here, 0.05. So that's 1.6, 1.645. 1.645. 0.45. And you would just times that by the same numbers over here. Now you're better off, right? Now you got like a 3% error. But it still doesn't seem good enough, right? When you want to publish your results and you want to say that, we have a 95% or a 94% efficacy with our vaccine, and you want to be at, 99% confident, let's say, at the minimum. Usually it's 95%, again, in standard and industry. I'm not sure what the vaccine confidence interval industry standard is. I'm going to guess it's 95 or 98 or something like that. But this still seems too high. And so the only way that you're going to get an acceptable error rate is by increasing your sample size. And so that's what they're doing, right? As this is an ongoing study, they're continuously gathering this data as people from the clinical trial come back and get sick. Eventually your sample size increases to an acceptable level that'll decrease the error. So here's here's the kind of the real follow-up question is, how big of a sample do you need? And let's say we need to be 99% confident. And you can also establish the error, right? How big of a sample do you need to be 99% confident that your error is within 1%? This is the real money question, right? This is the real engineer statistics master question, right? Your sample, how long do we have to wait? How big of a sample do we need? This is the real question of all of statistics. And so the way you would solve that is by using this formula here. It's just a rearrangement of the equation we have been using. But it's right here. Proportion where P and Q are known, or you can also do a proportion where P and Q are not known. And so in this case, we know P and Q because we've been doing the experiment. And so let's say, assuming that the proportions stay the same, assuming a 94% efficacy rate continues, what would we need? And then if we said we don't know what they are, we could do this. But let's see this, right? Let's say we know them. Let's say it stays at 94%. How big of a sample do we need? We would use this equation here. And so let's use the Z-score. So what's the Z-score for 99? Well, the Z-score for 99, we did that last time, I believe. Right, so that would mean I need something 0.005. Right, with 99, our alpha value is 0.101. So alpha over 2, 0.005. And when you look that up, and again, let's assume that we have the same values here. So an error within 1%, again, make sure you convert this to a decimal. So this is going to be a large number. Right? 2.575 squared times 0.944 times 0.056 divided by 0.01 squared. This is going to be 3,505.2 people. And as I mentioned last class, make sure you round this up because it's a discrete value. So the answer would be, we need to test a minimum of 3,506 people to be this confident. Now, of course, that's going to decrease if we only need, what if you only need to be 95% sure, right? Again, what if the question and the industry standard is more like 95%? Again, the 95% confidence interval is the most popular one. So let's say it is 90, let's say they only had to be 95% confident. How would that change? Well, all you do is you switch out your Z-score. Now you say the Z-score of 95 is 1.96. I know that because I use it all the time. It's not that much more forgiving. 2,030.8. So the clinical trial has to keep going and keep going and keep going, and you still have to show this in order for you to say, and you publish your results and you say, we have 95% confidence that it is this value. So again, you just got to wait until this many people get sick, and I'm pretty sure they're at that point now. Again, these people have to be enrolled in the clinical study to begin with. So you have to wait a while.